Thank you. So there's been a number of talks at this ICFP on algebraic effects and handlers. And mostly they've been motivated by doing things inside a pure functional context. Whereas today I want to talk about some work we've been doing as part of the multi-core camel project using algebraic effects and handlers to structure imperative systems programming. So to motivate these, we look at error handling. So in a piece of imperative code, if it detects that an error condition arises, then you could decide what to do. You could decide to log a message to continue or to quit or something. But often the correct response to an error is defined not by the bit of code that you're running, but by the context, by where it was called from. So for this reason, many languages have exception handlers, where instead of deciding what to do at that point, you can raise an exception and then decide what to do with it further out. So in some surrounding context, you decide what is the correct response to this condition. But sometimes the correct response to the error condition is regretting raising the exception in the first place, because you actually, once you raise an exception, you've thrown away whatever you were doing, and in the handler, you've no way of going back. So like all problems in programming languages, this was solved by Common Lisp in the 80s. Yeah. In the restart system, where you could just resume from an exception. But the thing, from this point of view, the thing that algebraic effect handlers get you beyond the ability to just restart is to name things. You can actually give a name to that computation that has been paused. And then in the effect handler, you can specify that when you're continuing. So it's not just resume the thing that was paused, it's resume this particular computation. So once we can name them, we can have more than one of them. And that means we can start switching between multiple computations and interleaving them. So that means that schedulers become a thing that we can write in OCaml code, in very lightweight user-level code, rather than something being baked into the middle of an operating system or a runtime. So here is a very simple implementation of a run queue. There's a queue, you can add things to it, these Ks are continuations, or you can remove something from it. If the queue is empty, you just stop. If there's something on the queue, you do that. So with that fairly trivial queue implementation, it's possible to implement a scheduler. We define two types of effect. Threads can yield, threads can fork off new effects. Sorry, fork off new threads. The scheduler wants them, waits them to do something. If they yield, it's fine, something else in the run queue. If they fork off a new thread, then that just gets added to the run queue. Or in fact, this particular implementation adds the current computation to the run queue and immediately does the newly spawned thread. So this is a very lightweight way of writing, writing schedulers and describing multi-threaded or describing current programs. And it's actually really useful to have this level of control over the scheduling policy. So, as a quick example, here's just exactly that code from the scheduler. And except it just counts the number of context switches it has done. And here's a very simple program which just forks off a million of those and runs those using the scheduler just defined there. So we can run those, and it does makes a million threads and does the million context switches. And so what I'd really like to show today is not like absolute performance numbers or something, because this is very much a system that we're still developing and we're doing lots of performance work on. What I want to show is the impacts that you can have by changing out scheduling policy. So this is a very simple scheduler. It's a stack instead of a queue. It's just as trivial as the previous one was. But just by changing from the stack to the queue for this particular program, it goes much faster. And this shouldn't actually be very surprising. The stack-based implementation there, whenever the thread yields, it becomes the next thing to run again. So we don't have to have lots and lots and lots of different threads and be constantly switching from one piece of memory to another piece of memory and going through all of them, keeping them all live. We just do the work in a last in, first out way. So being able to choose the scheduling policy is a big deal. If you want something like low latency, then you might want a queue. If you want just to get through a large amount of work very quickly, and if you care about throughput, then you might want a stack. And in conventional systems, you have to pick one of those, and there are good implementations of these. There are highly optimized schedulers that are low latency in operating systems. There's a highly optimized stack-based system in, say, Silk that can get through work very quickly. But the thing that you get with this style of programming with algebraic effects is that you can mix them and match them and compose them. We can have a low latency web server system using queue-type scheduling, and some of its requests can call a stack-type scheduler to do something while running. So because algebraic effects are scoped, because there's the body of the match is the only place where this scheduler's decisions actually are in force, that means they compose much more nicely than systems based on having a global scheduler and trying to interact with it. So another case where algebraic effects make this sort of imperative systems programming much more pleasant is in doing I/O. So the oldest I/O interfaces are these sort of direct style I/O, which are, there's a function called read, and it returns some data. And this is easy. This is pleasant to write code. It's very straightforward and simple and direct. However, on many systems, the more efficient means of doing I/O is actually to use callback-based interfaces, where you separate the beginning of an operation and something else to do when the operation returns. So initially, that ongoing represents not the result of reading something, but an asynchronous read operation that has begun but has not yet completed. So this style of programming is, I mean, you can do it, but it's a lot less nice than being able to write everything in direct style. Nonetheless, people do this, not in Camel, but also in JavaScript, C#, C, lots of languages. People rewrite their code into a very callback-heavy style in order to get the performance benefits of doing I/O in an asynchronous style. But with effects, we can implement that direct style code in terms of the callback-based interfaces. The implementation of read is to perform an effect that a read is happening, which is matched by a handler that registers the callback, and when the callback returns, it resumes the continuation. So this ability to, at user level, pause and resume threads very efficiently means that a lot of systems, low-level operating system interfaces that are quite difficult to use correctly, or quite tricky to restructure your code around, become much easier to integrate into simple direct style code. So there are some differences here to how we think of effects compared to the algebraic effects that have been talked about in various ICP papers. The biggest one is this notion of linearity. Our continuations can only be invoked once. And that again is driven by the sort of systems programming that we're trying to do with these things. The thing is, at the point where you perform a continuation, first, programs written in systems programs written against operating system interfaces often hold resources in local variables. Here, there is an open file. The open file is passed to parse contents. And that code is written so that no matter what parse contents does, if it returns a value or if it returns an exception, then when it returns, the file will be closed. But if we're allowed to invoke continuations more than once, then what if parse contents performed an effect and we grabbed a hold of that continuation? This is okay, parse contents could pause in the middle of operation, and then later on we resume it. Again, okay, eventually it finishes and it closes the file. But if we take that continuation and we resume it again, then it's going to try to access a file handle that has already been closed. So, and this is a problem that has been run into before, for instance. This is the reason for the online protect and dynamic wind friends in various scheme implementations. But those all require programmers to adopt a different model. This code is already quite sensible. We don't want to break that code with effects. So what we're doing is we're demanding that all effects are linear. Sorry, all continuations are linear. They can be used only once. So we don't have a linear type system in our Camel. We're already adding enough junk as it is. So we fake linearity dynamically. Each continuation has a flag, and if once it's invoked, we set the flag, and you get an exception if you try to invoke it twice. This hasn't been a problem in practice because it's quite easy to. It's not been an issue that we've been running into this exception happening very often, but I would prefer to be able to check it statically. The other advantage of linear continuations is that they can be implemented incredibly efficiently. If you know that your continuation is never going to be reused, you don't have to support general call CC, then you can use a standard stack. The continuation is just the stack pointer. Performing an effect just switches back to a different stack and resuming switches back to the stack that was paused. So effects generally are quite useful at allowing us to make use in a nice scoped way of these quite low-level and difficult to program operating system interfaces. And there is no operating system interface which is more nasty to program than asynchronous interrupts and Unix signal handlers. So you might want to do these in order to be able to interrupt long-running, purely functional code that's not reading any mutable states, so there's no means of communicating with the outside world when it's running. So if you want to handle Control-C in such a thing, then the standard way of doing that in systems based on Unix API, or which OCaml inherited, is to use signal handlers, where there's a global current callback, and you set the current callback. And ensuring that this is scoped correctly around the piece of code that you think should be cancelable is remarkably tricky. You're dealing with a higher order mutable state and asynchronicity. So by describing Unix signals as effects that are performed asynchronously, that your program is interrupted with a perform statement, then we can use the standard match syntax to bound the extent where the signal handler applies, rather than dealing with setting up the signal handler and tearing down the signal handler and making sure that those match correctly. It's scoped using a standard scoping that the rest of the language uses. So in summary, effect handlers are a nice means of interacting with these low-level operating system interfaces and are much more pleasant to deal with than directly writing callbacks or signal handlers. They're a really useful tool for systems programming. They allow us to do these mixing and matching of schedulers and interacting with low-level interfaces. And they save us from having to turn all of our imperative code inside out into a big mess of callbacks. Thank you.
If file I/O was also an algebraic effect, would you still have to have module continuation, or would it just be more efficient to have module continuation?
The question is, so yeah, if file I/O was
Also an algebraic effect.
was also an effect, then would we still need linear continuations, or would resuming them multiple times be okay?
Yes.
So we'd still really want linear continuations. You can. So there have been systems which allowed multiple shot continuations in the presence of things like file I/O. People have done this with dynamic wind and market, where you do things like when you re-enter the computation, you reopen the file.
No, but that's not asking, because when you're handling with a multi-shot, when you copy condition with clients, that handler should also tell you what to do with the file I/O, because it's also an algebraic effect. It's not going directly to the file system.
It seems like the problem is the interaction between built-in effects and algebraic effects. That's why you want continuations to be linear. Is that the case, or would you still want linear continuations only?
No, it's not that. It's it would still be just as bad with files as an algebraic effect. When you are holding a file handle, your context contains a linear object. It is incorrect, no matter how you've implemented it, to read a file after you've closed it. Whether close is
but reading is also an effect. So we still, if the handler that calls the project multiple times, should also make sure that you're not accessing the handler multiple times, right? Because it's also an effect. So, I guess we can take this offline and talk about it more.
Can you say anything about the implementation? So I'm guessing that I think OCaml does use a stack, doesn't it? So
Yeah.
you sort of, so I'm guessing that as a handler, you sort of maybe start a new stack so that you
Yes,
can stack
exactly.
it. Is that right?
Yeah.
So if you had very frequently nested handlers, then you might be starting new stacks all the time. But you don't have that capability. Is that
So we don't have that, but I don't think it would be too much of a problem. A new stack in our case is an allocation of initially, I think it's 32 words on the minor heap, so it's quite cheap.
Okay.
They grow as needed.
But typically you would start a new one when you get to a handler.
Yes, sorry. Every
Scope it.
time you get to a handle, we start a new stack.
Cool, thank you.
how do you compare this work with the work that Dolan was talking about on Monday? When he's doing similar kinds of
Yes,
things.
he is.
But he seems to be using
We're doing
continuation more than once.
We're doing remarkably similar kinds of things, and we discovered that we were both doing very similar kinds of things surprisingly recently. So yeah, we've certainly been talking to Dan a lot about this stuff. We haven't got a proper comparison of the two systems yet, but it's in the works.
What do you think of having both expensive and cheap effects? So you could have perhaps like install a hammer that can be given a continuation of multi-shot instead of one shot. Do you think you can mix the two in one system?
The trouble is that at the point where you perform an effect that will yield a multi-shot continuation, you need to know that there's no stack frame on the stack between you and the handler that's holding a linear resource like a file handle, which is difficult to guarantee without like static type system support. But in principle you could do that. In fact, we have a slightly hacky means of doing multi-shot continuations, which just does bizarre nonsense in the presence of file handles or references.
Okay, I might have a stupid question, but like, why is it better than, for example, LWT, where you like have a schedule and user space, where can like you are saving a callback and you are resuming it when something ready? What's the benefit?
So LWT has to do an awful lot more work to manage its calls and callbacks than ordinary function calls do. If I do a function call in a camel, then that pushes some, or puts some arguments and registers and jumps to the function call, and it uses its own space in the stack. If I do a callback in LWT, that creates an LWT object and registers the thing as a callback and allocates a closure for the continuation. And essentially, when you in LWT code, the context, the local variables are represented as heap objects, which is a lot slower than just writing direct style code. So essentially, what this gives us is the ability to run LWT style, that sort of callback type code, but using a standard stack rather than making
So
callbacks.
you are saying that like this effect thing, it doesn't create like a real closure.
Correct. The continuation objects K there are actually just the stack pointer of the stack that we're not running on anymore.
Okay.
Just put in the back.
Oh, that's good.
So yeah, Simon asked about the implementation, and you said you allocate stacks on the heap. Does that mean that I require garbage collection?
Can you repeat the question, please?
So since we allocate stacks in the heap, does that mean that we require garbage collection? So there's an interesting design choice here about what you should do with a lightweight thread that gets stuck. For instance, it's writing to a channel that nobody cares about. So we're taking the point of view that that's not an error, because you can write interesting programs that generate infinite streams, put them onto a channel. But for that to make any sense, we need some means of garbage collecting the ones that do so. So for the exact semantics we're going for, we do need a garbage collector. But if you chose to build a system where threads deadlocking is an error and threads must run to completion, then I think you could do this sort of stuff in a non-garbage collected setting.
But it's worth saying that under all of these scenarios, you've got to know exactly when a stack becomes free. Right? So you could use a sort of malloc free kind of allocator of stacks, couldn't you?
Yes, sorry,
So you don't need a kind of full-blown garbage collector.
Sure, great.
So
There might be, I'm not saying the good thing, it's just that you do know when they become free, unlike...
So that's what I'm saying, if you adopt the semantics where threads are supposed to get to the end and terminate, then yes, you can just free the stack when the thread finishes. But if you want them to be like collectible when they are writing to a, in Haskell's case, a dead end bar,
Yeah.
then you need the GC.
Yeah.
Any more questions?
Okay, thanks. Speak again.